A very good day to my lecturer and also my fellow friends. So today we are going to present, we are from BERZ, we're going to present our assignment from subject control principle BERA 2364. This is our assignment. Our lecturer is Dr. Shahratul Izzah binti Samsudin. So before that, I'm going to introduce my group members. So we have 4 of us. So first is Pulitan. So me, myself, second is Nanda, third is Azim, and fourth is Prem Kumar. The first part is introduction.
Introduction. So the introduction for this one is actually control system is actually widely used in electrical and also electronic engineering application. So as you can see, it's actually is to regulate system behavior and also to achieve desired performance specification. So as you know, this control system is actually a system which it managed to control all the behavior of another system. For example, we have air condition system which it controls the room temperature. Car cruise control the maintenance speed. A robot arm is to control the position, and also power supply is to control the regulating voltage. So without this control system, the system may be unstable, the output may be inaccurate, and also the performance of output may be very poor. Sorry. So the next part is the system modeling. So when you see the system modeling is actually to investigate an electrical system using the mathematical modeling. So you see, if you see the system modeling is actually converting a physical system into a mathematical equation. So in this project, you can see that the electrical circuit is converting into a transfer function. So this will make the analysis to be more easier. Okay, so the next part is the stability analysis. So it's access system stability using the root hood creation. Okay, so this one actually tells us that a stable system is actually a settled to a fixed value, and an unstable system is also grown without a limit. Okay, so we're going to see the transient response. So transient response actually refers to a behavior of the system immediately after an input is applied. So as you know, the most important parameter in this transient response analysis, later we will see the according slide, is the rise time, peak time, settling time, and also overshoot. So these are the parameters help us to determine the system's performance. So we also can see the controller implementation and all. So next we're going to go forward background study. Okay, so this is one of the main part is also in our in our assignment lah. Okay, so the background study. Okay, so this is one of the main part is also in our in our assignment lah. Okay, so the background study. Okay, so this is one of the main part is also in our study. This is the slide for background study. So the background study is actually a system. Okay, we go for the system modeling. So the system modeling represent the system mathematically. So the reports actually states the first stage in control system, which it analyzes. It control system, which is analysis is system modeling. So the system modeling is a process of converting a physical system into a mathematical model. So the purpose is why this modeling. Why they are doing this system modeling, because it's to predict system behavior, analyze the system performance, design controller, and also perform simulation. Okay, so instead of testing a real circuit repeatedly, these engineers will normally can analyze easily by using the mathematical model to understand how the system will be work later. So the next part we're going to go for the unit step response. So the unit step response is actually apply a unit step input to the system, and it's also observe the output response over the time. So this report explains that one of the most common methods for evaluating system performance is the unit step response. So this is one of the important steps also. So its unit step response suddenly can change from 0 to 1 at the time of t equals to 0. So this is also very important, and the system output is then observed over the time. So this allows the engineers to study how quickly and accurate the systems respond to an input signal. Okay, so this is the important part also. So here we have the peak time, settling time. Okay, later you will see in our next part. Okay, so now we're going to present our first part, which is part A. Part A is the system modeling, okay, of this assignment. Okay, so this is which is part A. Part A is the system modeling, okay, of this assignment. Okay, so this is which is part A. Part A is the system modeling, okay, of this assignment. Okay, so this is which is part A. Part A is the system modeling, okay, of this assignment. Okay, so this is which is part A. Part A is the system modeling, okay, of this assignment. Okay, so this is which is the circuit that we receive from our assignment. So you can see this circuit here. So if you want to know, the objective of this section is to derive the transfer function of the given electrical system in the frequency domain. So the transfer function represent the relationship between the output voltage, you can see the formula here, over the input voltage Vi in the Laplace domain. So this is also very important, this formula, which we will use this formula later on for the calculation of this circuit. So as you know, this transfer function is actually very important for all the engineers because it allows us to study the dynamic behavior, stability, the transient response, and also pole zero location. So this is also we go through later. So why we are using this frequency domain? Okay, so this circuit, why we are using? Because this circuit has resistor, inductor, and also capacitor. So this behavior of this inductor and capacitor is normally described using different equation. But the equation is not available in the slide, as you know, di over dt. Okay, for capacitor is C dV over dt. This one you will see in the next slide, which will explain about the equation. Okay, so the derived the transfer function, the circuit first is converted into the Laplace domain, where the inductor and capacitor represent by their own representative. Like I said, for inductor we use L di over dt, and for capacitor we use C dV over dt. You will see this in our next slide. Okay, so we also using this Kirchhoff law. Okay, so this Kirchhoff law is very, we also apply this KVL, Kirchhoff voltage law. So why we apply KVL? Because after we converting the circuit into the Laplace domain, KVL, Kirchhoff voltage law, is used to derive the mathematical equation. Okay, so KVL states that what? Okay, what's KVL states? So KVL states that the algebraic sum of the voltage around the closed loop is equals to zero. Okay, so we can use these KVLs to relate the input voltage, the output voltage, the current, and also the components impedance. So this is also very important. Okay, so the transfer function is very important, describes the dynamic behavior, okay, of the system. It is used to analyze the input. Okay, so next we're going to go for the theory calculation for this part. So this part is going to take a bit long, so because we are going to go explain step by step. So we have first loop, and also we have two loop over here, loop number one, loop number two. So we have given r1 equals to 2, r2 equals to 2 ohm, is equals to 2 h, c equals to 2 farad. Okay, so you must know all of this, and you have to convert it all to Laplace domain. Okay, you have to convert it the L and also C to Laplace domain. Okay, so if you can see, you have to convert the components into, like capacitor, you have to convert it to Laplace domain. So the capacitor value we have given C equals to 2F. So when you convert to Laplace domain, it will become 1 over 2S. Okay, why we have to convert it to Laplace domain? Because the Laplace transform converts the circuit into an impedance network, so allowing us to apply circuit law more easily. That is why we convert it to Laplace domain. Okay, we also have to do the Laplace domain for L equals to 2h. Okay, so when you substitute L equals to 2, so your ZL will become 2s. Okay, the S is very important, you have to put at the back. So the next one, we have to define the current. Okay, so we have Is. So the Is is the source where the current is flowing from the input to the branch. Okay, and I2, we have the current flowing through the inductor capacitor from here to the capacitor branch. So step number 4, this is where you have to do the equation. Okay, so we just apply the KVL. Okay, I'm going to go to the next slide. Okay, so this is where we apply the KVL to this left loop. Okay, so this is the left loop. So this is where the current flow. So is r1 plus is equals I2s, then you close with the bracket r2. Okay, so this, so you simplify, you just put the value back. So is is 2I plus is here is 2is minus I2 over s. Why we have to put I2 over s? Because it is in the middle of in the middle of loop I1 and I2. So it's the middle. So it's sharing the loop with I1 and I2. After you finish the left side, you have to do the KVL to the right side. It's the same. Okay, so you do to the left side first, and also you do to the second loop the same thing. I2s, this is where the current flow, go to ISR2 resistor 2. I2s, this is ZL is the inductor. Okay, so then you'll get these two equation. Okay, equation 2 and equation 3. So then we have to do equation 4. So what is equation so 4? So equation 4 is VO equals to I2S over 2S. So you just substitute the value to I2, you just substitute the value of I2 is 2IS. You have to substitute equation 1 into equation 3. Okay, so your equation 1 just now we get 4is minus 2I2. So you substitute into equation number 3. So equation 3 is 4is over 4si square plus 4s plus 1. So this is the substitution lah you have to done. Okay, this part you have to do so you can understand more deeply. If I explain also, maybe some of us can't understand. Okay, so we just go through the substitution only, not so detailed. Okay, so this part, the substitute, we'll substitute 1 into 3. So after you substitute, you get the final answer for equation 4 is 4si over 4s square plus 4s plus 1. So at this stage, I2, the current is expressed entirely in the terms of is. Okay, so this will reduce the number of unknown variables and simplify the derivation. So easy for you to do the calculation. So the next step is you have to substitute equation 4 just now into equation 2. So this is your equation 4, this is your equation 2. Okay, you substitute over here, which is the 2 4 si's. Okay, you have to substitute, then you factorize the same value 4. Then you will get a new equation, which is is. This is the new equation. Okay, so this equation is now expressed in the input voltage entirely in the terms of the source current. Okay, so only one variable will remain over here. Okay, so hopefully you all understand. So the next part is we're going to obtain the output voltage. Okay, so the output voltage formula is VOS equals to I2S over 2S. So you just, from the first equation, so you just substitute the value. Okay, so you have your I2, just now we calculate it 4SIS, and you have the 2S is 4S square plus 4S plus 1. So you have to divide it, you have to times it. Okay, 1 times 4, 2s, here you have to times with 4s times 4 times here, you'll get this 6 equation. Okay, so after then, therefore you get this gs. Okay, this is the important part lah. This is the how you want to form the transfer function. So gs is equals to vo over vis. So this is the important part over here. You just substitute the value that you get vo just now and also vi. Okay, vi, how much you get? You get is 16s square plus 86 plus 4 over 4s square plus 4s plus 1. So this equation, this is not the end. You have to times, you have to solve this equation. Okay, how you want to solve? You have to solve it until you get an equation. Okay, you will get the final one, you will get 2 over 16s square plus 8s plus 4. So that's the final equation. Okay, I haven't put over there, but it's okay. So that's the final equation. I repeat, the final equation, once you times, you will get 2 over 16s square plus 8s plus 4. So that's the final equation, that's the final transfer function. So then later, after you do this calculation, we want to check the output in our MATLAB, sorry, we have to put the value in our MATLAB. So as you know, 2 will become the numerator because it has constant value, because there is no infinite zero. Okay, that is for 2. Denominator, as I said, 16s plus 8 plus 4. You don't have to write the s, you just write 16, you just write add 8 and also 4. Okay, you don't have to write s power of 2 s and all the algebra. You just write the value. Okay, so then you have to put the tf. Why we put tf? Because this is transfer function. Tf is the meaning of transfer function. Okay, and also you type step. Grid means is to make grid on your graph, and you write the title is unit step response of the system, because we want to find that unit step response of this system. Okay. Okay, so remember the G equals to TF is actually the functions of the transfer function model, which the MATLAB itself, it will convert the numerator and denominator into a transfer function object. Okay, so this command will tells the MATLAB which is GS equals to 2 over 16s squared plus 8s plus 4. But the formula, you don't have to put all together. You just put the numbers only in the MATLAB. Okay, so next, we just type step G. Step G is actually it's to create and also to generate the graph, the response graph. Okay, so we will go for the next slide, which is the analysis of the input. So this is the graph output. I hopefully you can see because I can't zoom over here. Okay, so we will explain from the graph lah. So you can see t is equals to 0. So you can see the rising region over here is actually after the step input is applied, the output begins to increase gradually. So this will indicates that the system is responding to the input signal, and also the response continuous rising towards the state value. Okay, you can also see the peak response. Okay, there's a peak response here. So the graph shows a maximum output value approximately around 0.581, which is around like 7.18 second. Okay, so this point is the peak point. Okay, I can show you here, but it's not labeling. Okay, okay, this point. Okay, this is the peak point. Okay, the peak point. Okay, so next we're going to go for the overshoot. Okay, the overshoot is 16.3. Okay, the 16.3%. So if you the overshoot is the final overshoot, we can see it's reaching around like the peak overshoot is reaching around 0.581, if you can see from the graph, and also before settling. So this means that the response is exceed the final value. So the final percentage overshoot also you can just find. You can just take the you can just take the peak deviation value, you minus 0.5. So 0.5 you minus with 0.581 and you divide by 0.5, you times with 100, you can get the percentage overshoot. So overshoot is around 16.3. You can use this as formula like just now I explained to find the percentage overshoot, or you can get the final answer from this graph itself. Okay, if you don't want to count, you can just find from the graph itself. Okay, so so this is the part lah. So you can see the settling region. Okay, you can see the settling time region here. So as the time increase, the oscillator gradually decrease. Okay, when you can see the time increase, the oscillator gradually decrease. So you can see the response is actually near to 0.5. Okay, the response is actually near to 0.5. It's actually approximately around 16.2 second. It's here. 0.5. Okay, so the set time second is 16.2, so the time here is around like 16.2 second. Okay, so the final value of the graph is a 0.5. So why we are telling the final values? Because this is uh, the graph agrees with the value obtained. Okay, so this is the MATLAB this one lah. Okay, if you want to be more sure, you can also go for once you press enter at the MATLAB, it will show the values accordingly lah. Okay, so you don't have to calculate. If you want to, if you calculate theoretical part and you want to compare your answers in MATLAB, once you put the MATLAB code, once you press enter, so this is the answer you can get. Okay, so you can check your theoretical answer is correct or not with the MATLAB answer. All right, so next we're going to go for the analysis. This one lah. Okay, this one I think I already explained lah, because it's the same I explained just now. Analysis of the unit step means we are explaining from what we get from our output lah. So based on the graph, the MATLAB result, the system actually inhabits an under second order response. Okay, so this is actually indicates the presence of the overshoot and also oscillation before reaching the steady state value. Okay, so as you know, this response initially rises from 0 until it reaches the time rise time approximately, as you can see just now, 3.28 second, and it's also continuous to increase until reach the maximum peak at 0.581. Okay, I cannot go back because it will pause the slide later. Okay, so that's all. Okay, so the next part, after reaching the peak, okay, the response gradually decrease and oscillation around the steady state value. So this oscillation reduce with the time due to the damping present system. Okay, so as you see the last one, you can get 16.2 seconds. So this is the response eventually settle at that second. Okay, so the final value of this response is 0.5, which matches the theoretical steady state gain obtained from the transfer function. Okay, later we'll confirm with the theoretical calculation. Okay. So this is the part that I said, the MATLAB command window. You can check the answer. If your theoretical answer is correct with this, okay, then you are in the safe track. Okay, so you can see the rise time, settling time, like I said just now, settling mean. This is important. The important part is rise time, transiting time, settling max, peak time. This is the, so the answer is 0.5. This one you can do calculation later. We will guide you one by one. Okay, so this is the part that I said, the MATLAB command window. You can check the answer. Okay, so now we're going to go for identify the location. Okay, so we're going to identify the location of the next question is the location of the poles and also the zeros of the system. So after analyzing the unit steps and response, so we're going to analyze the next step, which is to determine the location of the poles and also zeros of the system. So pole zero analysis is very important because it provides information about system stability and also dynamic behavior. Okay, so the objective of these polls is actually, the purpose is actually of the section is to identify the zero where the value of s that makes the numerator equals to 0, and also the poles is actually the value of s that makes the denominator equals to 0 too. By determining this value, we can understand that stability, oscillation, and also response speed, and also overall system behavior. Okay, so so we're going to explain about this MATLAB code over here, as you can see in this diagram. Okay, so we are using the same. The numerator is 2, the denominator is 16, 8, and also 4. You can see from here. So we define G equals to transfer function. We're going to use transfer function formula. We are giving the command to the MATLAB. We are using 0G. Okay, 0G explains that it calculates the zeros of the transfer function, which MATLAB will examine the numerator and also determine of all the values of S that makes the numerator equals to 0. So result are stored in the variable. Okay, it will store the value of z, and also we put pole g is also a command that calculates the pole of the transfer function. Okay, so then we write there 0 of the system. Okay, this disp is the 0 of the system in the command. This is nothing. Okay, so you just do like normal lah. Okay, you have to type figure pz map. Okay, pz map is to generate the pole 0 map. Just now we gonna generate graph. Okay, but this one we want to generate the polo 0 map. Okay, and you press grid on so that you have a grid on your graph. Okay, so the title we change to pole 0 map of the system. So this is the MATLAB output. Okay, you can see this is the MATLAB output. So from the MATLAB output, you can see after executing all the MATLAB code, this is the windows will be displaying. So the output actually indicates zeros. Okay, no infinite zeros are present. Okay, how about the poles? The poles is actually a two complex conjugate poles are obtained over there. You can see. Okay, so the MATLAB is output confirms, this output confirms that the system contains two poles and no finite zeros. Okay, so if you want to understand this pole zero map, is actually the pole zero map consists of two axes. Okay, we have horizontal axis and also we have vertical axis. Okay, so the horizontal axis is represent the real axis. The real part of a pole determines whether the system is stable or unstable. Okay, we go back to the vertical axis. So the vertical axis explains the imaginary axis. So the imaginary axis is a part of a pole which indicates the oscillator behavior of the system. Okay, so this is the pole location of this. Okay, so the poles are located symmetrically above the real axis because they are form a complex conjugate pair. So the poles appear as cross x, the symbol x. Okay, you can see the symbol x over here. Okay, it's because they form a complex conjugate pair. Okay, I can label here, this is x, this is x. Okay, it's in the vertical axis. Okay, so that's all for this side. So the stability so when you see the pole zero map shows finite zero, so this is because why it shows finite zero, because this is because the numerator of the transfer function is a constant value and therefore does not produce any zero location. So as a result, no zero symbols appeared on the graph that we see. So the stability analysis from the pole zero map, we can see the poles have negative real part, which is negative 0.25. Okay, this is quite important also. All right. So okay, so since both poles are located on the left hand side on the complex plane, the system is stable. So why is the system stable? So if you ask why is the system stable, because for a continuous time system, poles in the left half plane is stable, poles on the imaginary axis is marginally stable, and poles in the right half plane is also unstable. So this is why we can define it, the system is stable. Okay, okay, you can see from this graph. Okay, so next we're going to explain about the oscillator behavior. So actually the poles contains the imaginary components, which is j 0.433. Okay, this one we will do we will get the equation later. Okay, we will get the equation later. Later we will do theoretical method of this equation to get this value. Okay, why they said plus minus j 0.433. So this is the presence of imaginary parts that cause the system response to oscillate before settling. So the observation agrees with the unit step response graph obtained earlier, where the output exhibit overshoot and oscillation before reaching the steady state value. You can see from this observation. So you can see relationship with the unit step response just now from the part A number 2 that I showed. The unit step response shows overshoot approximately reaches 16.3, oscillator behavior final settling is 0.5. So these characteristics are consistent with the pole location obtained from the pole zero map that we see over here. Okay, so the complex conjugate poles explains why the response oscillates, while the negative real parts causes the oscillates to decay over time. All right, so all right, so now we're going to go for the theoretical part. Okay, so this is the theoretical part, calculation for the poles and zero of the system. So just now we find by the MATLAB part. Okay, we get the answer. Okay, so the theoretical part calculation for this, so you can see here we are using the same thing. Okay, the same gs value just now we obtained at the first question. Okay, so your numerator is 2, so 2 is when you want to find the zero, so 2 is automatically equals to 0. Okay, so your a is 4, your b is 2, your c is 1. So we are using quadratic equation. Okay, we are doing the quadratic equation. Okay, let me show you the next slide. Okay, this is the quadratic equation. Okay, so most of us have studied this quadratic equation. So as you define the a, b and c, so you just substitute the value over here. Okay, you just substitute the value. Okay, you just press your calculator for this quadratic equation and you will get a 2 value. That's why we put plus minus. Okay, you will receive a 2 value. Okay, from the quadratic equation you will get s equals to negative 0.25, negative j 0.433. You'll get two values over here, okay, from the quadratic equation. So the real part is actually negative 0.25. The imaginary part is positive by negative plus minus 0.433. Why there is plus minus? Because you're getting two values from them. So the meaning of real part is what? So the meaning of real part is actually, since the real part is negative, the response decrease with the time. And the imaginary, what is imaginary part? So imaginary part is the components produce oscillatory behavior. So this explains the components, why the unit step response graph showed overshoot, oscillation, and also gradually settling. So from this observation, we can see the theoretical calculation shows that the system has no finite zero, two complex conjugates. The negative real parts of this poles confirms that the system is stable, while the imaginary parts explains the oscillatory response in the MATLAB simulation. So now we're going to go for the last final slide for my presentation, which is the comparison between the theoretical and also the MATLAB result. All right, we are going for the next slide. So this is the next slide. This is the last part for my section. So we are going to discuss on the table. So you can see the parameter. We are going to show you the theoretical result and also the MATLAB result that we obtain. So I have shown you the theoretical result and also the MATLAB result calculation. So the transfer function obtained is 2 over 16s squared plus 8s plus 4. Okay, so the same transfer function is implemented in the MATLAB using transfer function TF in the command of MATLAB. So this confirms that the MATLAB model accurately represents the electrical system derived from the circuit analysis. So from the zero analysis, both of the theoretical calculation MATLAB and result indicates that the system no infinite zero. You see, this is none over here. Okay, so this is because why? This is because the numerators of the transfer function in a constant value of a 2 and does not contain the variable of s. So that is why there is no value of s. That's why we said 0 at this part. Okay, so next this part is the pole. Okay, okay, the pole we have the pole 0 negative 0.2. Pole number 1 we have negative 0.25 plus j 0.433, and the second pole we have for the MATLAB result is the same. Okay, so this command is exactly the same pole location. So this agrees that the verify of the accuracy of the both transfer function derivation of the MATLAB simulation. So this pole location is actually is provide a very important information about the system. Okay, so because both poles have negative real part, which is negative 0.25, you can see from this table. Okay, which means the system is stable. Why the system is stable? Because the response will decay with the time and eventually reach a steady state value. So in addition, the presence of imaginary components, which is J 0.433, indicates oscillatory behavior. So this observation that we see is consistent with the unit step response graph, which shows the overshoot and oscillation before settling at the final value. So overall of all of this conclusion, the theoretical and also the MATLAB result are confirmed completely is a good agreement. Why we said that? Because the identical transfer function, the pole location, the zero location, confirms that the system model is accurate. Both is accurate. We have seen from the theoretical and also from the MATLAB. So both is accurate value. Okay, that the MATLAB simulation is also successfully showed the validates the theoretical analysis that we do. So from the observation that we see the comparison for all of these, the comparison shows no different, okay, between the theoretical calculation and also the MATLAB result. So therefore, the derive of the transfer function is verified is to be correct. Okay, so means we did from the MATLAB simulation and also the theoretical calculation, we did both is correct. So the pole zero is also analysis is confirmed that the system is stable and inhabits the underdamped response, which agrees with the characteristic observed in the unit step response analysis. So that's all from my part. I will pass to my next team members. Thank you.
Hi, my name is Muhammad Hazim bin Ahmad Shairi, and my matrix number is B122410749. So I will continue our presentation for part A, state space representation. So this will continue from part A from Nanda. Okay, let's begin. Hi, my name is Muhammad Hazim bin Ahmad Shairi, and my matrix number is B1224. Let's start with the basics. What exactly is? Fundamentally, it's a time domain model used to mathematically describe a dynamic system. Unlike traditional methods, it breaks the system down into a set of first order differential equations and heavily utilized matrices, specifically matrices A, B, C, and D, to completely map out the system states. Now, you might wonder, why not just stick to classic transfer function? Well, while transfer functions operate primarily in the frequency domain and treat a system like a black box, state space models pull back the curtain. They capture the raw internal behavior of the system through explicit state variable, giving us much deeper insight. Okay, next, let's look at the mathematical architecture under the hood. The core model is driven by two main equations, the state equation, which is axt plus but, and the output equation is yt is equal to cxt plus dut. Breaking down our variable, xt represents our state vector, ut is our incoming input signal, and yt is the final output. The behavior is dictated by four core system matrices. A governs the internal dynamics, B dictates the input handling, C maps out the output transformation, and D manage direct feed through. To bridge the theory and practice, we can easily convert classical transfer functions into this format via companion form manually, or be simply using the TF2SS or SS command in MATLAB. The real advantage here, it handles complex multiple input, multiple output, supports modifications for non-linear system, and models time varying environmental beautifully. So, so we go to the next, which is the theory calculation. Let's put the theory into practice with a concrete calculation. Suppose we are given the transfer function. Okay, we can see first GS is equal to 2 divided by 16 s power of 2 plus 8 s plus 4. Our first goal is to convert this into state space representation. So step 1, we need to normalize our highest order CS system by dividing both the numerator and denominator by 16. We simplify the function down to GS is equal to 1 over 8 divided by S power of 2 plus 0.5 S plus 0.25. Step 2, we compare this directly into the standard second order transfer form, which is GS is equal to B0 divided by S power of 2 plus A1S and plus A0. So for the step 3, using the companion form method, we map this coefficient directly into our matrix structures. The yields of our final state space answer matrix, which is A is equal to 0, 1, negative 1.25, and negative 1.5. The input matrix B is 0, 1. Output matrix C is 1 per 8, 0. And direct feed through matrix D is 0. Clean structure and ready for simulation. So we go through for the simulation, which is output. We need to produce the unit step response of the system. So with our matrices derived, we move from the page to the computer. Here you can see the MATLAB script used to verify our manual calculations. On the left, we define our newly calculated matrices A, B, C, and D. We pass them through the SS command to generate the system and use step, which is
sys underscore ss to plot the unit step response. The resulting graph on the right gives us the visual behavior of the system. You can see the amplitude smoothly rising over time, overshooting slightly, and eventually stabilizing beautifully around the steady state value of zero point 0.5. It, ro- it takes roughly 15 to 20 seconds to reach complete steady state equilibrium. So next, observation based on transfer function and state space modeling. So we go through for the TF first, which is for the frequency domain. It relies on Laplace transformation, and for the input output models external relationships only. And for the system type, primar- primarily used for the CISO system, and analysis is used both Niquise and root locus. So for the state space, time domain is used for the first order differential equations, and internal states is analyzed hidden system dynamic, and for the system type is robust support for MIMO system, and for the application optimal control and modern design. And for the equivalence, identical result, which is both model produce the same output for identical inputs, and the software that use is MATLAB seamlessly convert between transfer function and state space for the matrices, some rise time, overshoot, and settling time. Alright, simulation with S theory result for the full MATLAB code. To ensure rigorous engineering validation, we wrote a comprehensive MATLAB script to explicitly cross-examine our simulation against analytical second order formulas. As you can see from the codes block, the left pane defines the raw system parameters, which is setting our naturally frequency and damping ratio both to zero point 0.5, which denotes an RDM system. The script calculates the precise theoretical values for the rise time, settling time, peak time, and percentage overshoot. The right pane handles the plotting data, extracting the step response matrix dynamically using the max function and mathematically threshold, and then physically overlays the theoretical markers right onto the response plot to see our maths match the simulation reality. Right. So next, and here is the visual fruit of the code. On the left, our output graph simulation shows exactly where does theoretical markers land. The green circle tracks our 90% rise time, and the red circle pinpoints the absolute peak time, and the purple circle marks our 2% settling time threshold. If you look at the command window at the right, numbers speak for themselves. The transfer function model and the state space model yield identical simulations metrics such as a rise time of 3.2781 seconds. Right below it, our raw theoretical formulas predict a rise of 4.84 seconds and peak time of 7.26 seconds. The overlay proof that simulation behavior and the mathematically predictions tracks other incredibly closely. So for the theoretical dynamical response, to, en- to anchor our baseline before the final comparison, let's explicitly highlight the exact number generated by our standard second order theoretical formulas. Given our system parameters where the natural frequency is zero point 0.5 radian per second and the damping ratio is zero point 0.5, the math dictates. So a rise time of exactly is 4.80 seconds, a peak time is of 7.26 second, the setting time is 1.16 second, and the maximum overshoot is of 16.4%. These matrices serve as our mathematical truths purely derived using a classical control theory formulas. So this is the result. So for the theoretical vs simulation comparison, so this is our last part. Finally, let's bring together all the ultimate comparison metrics. So when we stack the theoretical calculation side by side with the MATLAB simulation, the alignment is spectacular. The rise time shows a tiny variant under 1%. The peak time match our prediction closely at 7.3 seconds, and settling time is exactly the same at 16 seconds. And our overshoot comes in at near identical 16.3% compared to the theoretical 16.4%. What does this tell? The minor discrepancies are well within expected limits, purely due to numerical approximates in computer algorithm. This excellent agreement completely validates our manual mathematical models, confirm our state space conversion is flawless, and prove our MATLAB environmentally is highly accurate. Thank you so much. Now I pass to my friend.
My name is Punithan. So now I'm going to explain about part B, it is stability analysis. The objective of this part is to investigate and provide the stability analysis of the system Routh-Hurwitz method and compare the simulation result with theoretical value. My name is Punithan. So now I'm going to explain about part B, it is stability analysis. The objective of this part is to investigate and provide the stability analysis of the system transfer function. The given character equation is 2 over 16s squared 2 plus 8s plus 4. This equation is obtained from the denominator of the system transfer function. So first, we construct the Routh-Hurwitz table using the coefficient of the characteristics equation. According to the Routh-Hurwitz equation, all elements in the first column of the Routh table are positive. So there are no sign changes. And there are no poles in the right half plane. This indicates that the system is stable. ES simulation result. To verify the stability theoretically, we solve the characteristic equation using the quadratic formula. So first we need to simplify the equation. So we divide by 4. So then we use the quadratic formula to find the theoretical value. So the answer we get negative 0.25, the imaginary number we get 0.433. So the both roots have negative real parts, which confirm that the system is stable. MATLAB simulation result. The MATLAB simulation was carried out to verify the theoretical analysis. The simulations also show the same result as theoretical value. It's negative 0.25 and imaginary value is 0.433. These poles lie in the left and half of the S-plane, confirming the stability predicted by the Routh-Hurwitz equation. So, in the conclusion, the both Routh-Hurwitz analysis and MATLAB simulation produce the same result. The system is stable because all poles are located in the left half plane and there are no sign changes in the first column of the Routh table.
Hi, my name is Prem Kumar Naliki Sivakumar and my matrix number is B1224-155. So my part will be controller design. So this is the block diagram given in this question. So I will briefly explain what is control design. A gain compensator is used to improve control system performance by adjusting the system gain. which changes the locations of the closed loop poles. This directly affects important time domain characteristics such as rise time, settling time, and percentage overshoot. To achieve the desired overshoot range of 5% to 25%, the damping ratio should be maintained between 0.2 and 0.7, where a lower damping ratio provides a faster but more oscillatory response, while a higher damping ratio results in a slower yet more stable response. In this project, the gain is tuned to obtain the required performance, and the results are verified using MATLAB tools such as RLocus bracket, step bracket, and step info bracket. So now we have to find out the transfer function. The first step will be gs given, which is 2 over 16s square plus 8s plus 4. So we can bring out the common thing and then simplify, and finally we got 1 over 2 in bracket 4s square plus 2s plus 1, and then we use pre-amplifier times by power amplifier and times by gs, where k times 10 over s plus 10 times by 1 over 2 in bracket 4s square plus 2s plus 1. So the final output will be 5k over s in bracket s plus 10 and also times by in bracket 4s square plus 2s plus 1. So we got our transfer function. So now we're going to calculate the closed loop transfer function. So we assume h as 1. So the transfer closed loop function formula will be transfer function open loop divided by 1 plus transfer open loop function. So after we substitute the values, it will be 5k over in bracket s plus 10 times by in bracket 4s square plus 8s plus 1. So and then we should divide it by 1 plus 5k over s plus 10 in bracket and also times by 4s square plus 8s plus in bracket. So the final answer for the closed loop function will be 5k over in bracket s plus 10 times by in bracket 4s square plus 8s plus 1 and then plus by 5k. The next calculation will be overshoot. We choose the overshoot 10%, where the damping ratio equals to negative ln in bracket overshoot divided by 100, also divide by power root of 2 pi square plus in bracket ln in bracket overshoot divided by 100 and then close the bracket followed by square. This will be the formula for damping ratio, and then after we substitute all the values, the final answer will be 2.30 divided by power square root 15.17. After the calculation, 0.591 will be the damping ratio, and then followed by phase magnitude. The formula will be tangent power of negative 1 times by 2 damping ratio divided by power root square negative 2 damping ratio square plus power root square 1 plus 4 damping ratio followed by power root of 4. So after all the substitution, the final answer will be 80.66 magnitude. These answers are for the theory calculation. Later on, we will move on to the result we got from MATLAB. So now from the board plot, we got the magnitude phase, which is equals to 0.528 radius per second, and then the adjacent will be 6.64. To find out the k, we use the formula 2 log power of 10 k equals to the adjacent, which is 6.64. After the substitution, the answer will be k equals to 2.15. So since we got the value for k for the open loop part, the final answer will be, after the substitution, substitute the k equals to 2.1.5. The final answer will be, for the open loop, 10.75 divided by in bracket s plus 10 times by in bracket 4s square plus 2s plus 1. And also for the closed loop will be the same, and the final answer will be 10.75 divided by s plus 10 in bracket 4s square plus 2s plus 1 in bracket and times by 10.75. In the previous slide, I have attached the coding that we have used for this project to obtain closed loop gain and phase margins, and also open loop gain and phase margins through MATLAB. So first we will go through the closed loop gain and phase margin, which is the magnitude for gain is 32.3 dB, which is at 2.29 radians per second. And for the open loop gain and phase margins, the gain margin will be 25.8 dB, which is at 2.29 radians per second. And the phase magnitude will be 79.8 degree. For the transfer function open loop step response characteristics, we got rise time equals to 3.841 seconds, and for settling time, which is 16.2506 seconds, and for overshoot it will be 16.828%, and steady state value will be 0.5, and the closed loop transfer function, which is TS for closed loop function, will be 5 over 4s power of 3 plus by 42 times by s power of 2 and plus by 21s, and finally followed by plus by 50. For my part, finally, I will explain about the transient response analysis and observation. By applying a gain of k equals to 2.5, the compensated system successfully achieves the required 5% to 25%, which is they required in this project, overshoot with a slightly underdamped but well-controlled response, while simultaneously delivering a fast rise time, quick settling behavior, and robust stability backed by high phase and positive gain margins.
To wrap up, this project successfully brought together the core principle of control system modeling, stability analysis, and control design to analyze and improve an electrical system performance. So, we start by modeling the system using both transfer function and state space approach and confirm that both representation gave consistent result. From there, we evaluate stability using the Rouse Hartwig criterion and validate those findings against MATLAB simulations, giving us confidence and theoretical analysis was reliable. The main design goal was to achieve a 13% overshoot target. We did this by designing a gain capacitor, calculating the required damping ratio, phase margin, and gain from the both load data. The resulting compensate system met the performance target while staying stable. Overall, this shows that even relatively simple control strategies, when backed by solid modeling and validation, can meaningfully improve system behavior. That's the core takeaway. So that's all from us. Thank you.